All right, here we're going to learn about the greenhouse effect, a very natural process of sunlight traveling 93 million miles from the sun, traveling through space, and how it then affects the Earth as it strikes the surface and travels through our atmosphere. So there's a lot of parts that we'll need to make sure we pay attention to. We're going to be using light as the idea of pure energy, and we're going to be talking about how sunlight is in the form of shortwave photons or shortwave energy, and as it strikes the Earth's surface, it's going to heat land and water. It's going to heat them differently. They have different specific heats, therefore they are going to heat up differently. In light and dark objects, which we will call albedo, will also affect the ability for sunlight to be absorbed. So we can talk here as the greenhouse effect kind of plays out. Some of the light is reflected and some of which is absorbed. And the light that is absorbed and then re-emitted is going to be heating up our atmosphere by the form of long wave or infrared radiation. And that the heat that's trying to naturally escape the Earth is then retrapped by what we're going to call greenhouse gases. So that's the process that we're going to look at today, called the greenhouse effect. Remember light. Light is pure energy, that everything on the electromagnetic spectrum is just a form of pure energy. That visible light that we will call light rays from the Earth fall in the visible light spectrum, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. That these here are on the higher frequency, so therefore shorter wavelength. And that's why these are typically referred to as short wavelength. And therefore, after that light is absorbed within an object, the object is going to re-emit what's called long wave or infrared. This is just heat energy. It's just visible light that is absorbed that's re-emitted as a longer wave. So we use light to make sure that we understand this is the energy that's driving processes on the Earth's surface. So as the Earth is orbiting the sun, we have this axial tilt that different hemispheres are absorbing different amounts of sunlight energy, right? Because the axial tilt. So here we have the northern hemisphere summer solstice. Here we have the southern hemisphere summer solstice. In other words, the northern hemisphere's winter solstice. Here we would have our spring equinox, and here we would have our fall equinox. So each one of these pictures is really just showing that different amounts of direct energy are going to, well, let's just say, lead to different outcomes in terms of the total heat energy that is being absorbed and then re-emitted as infrared heat. So if I look at this picture here, we could see that the Tropic of Capricorn here, 23.5 degrees south, is receiving the most direct sunlight, right? 90 degrees are directly overhead, and the southern hemisphere is going to heat up proportionally, relative to this direct sunlight. Whereas the northern hemisphere is receiving a greater angle, and in this case it's going to be receiving less direct sunlight energy, so it's going to be colder. So we're looking at a couple different parts and pieces altogether. So we have sunlight coming in, it's heating the Earth's surface. The Earth's surface heats from the surface on up, it heats the air above it. Some of that heat that's trying to escape is trapped by these greenhouse gases, which I'll refer to as GHGs, greenhouse gases, GHGs. So here we have the idea of insolation, incoming solar radiation. This is kind of what is driving the heat budget here. That we have 50% immediately entering the atmosphere. It makes its way to the Earth's surface, and it is absorbed by the surface. And other parts are absorbed by clouds and ozone, water, dust, different substances that are found within the Earth's atmosphere. But some of it's reflected. Clouds reflect, right? Cloud tops are white. They make very nice reflectors, or they're kind of like mirrors that reflect these photons back into space. We get clouds and dust, just particulates that are reflecting sunlight, and some of which is reflected directly by the land and sea itself. So we have it's either being absorbed or it's being reflected. Of the 50% that makes it to the Earth's surface, 30% is re-radiated as long wave radiation. This is that heat energy in the form of infrared. The remaining 20% heats the atmosphere through both conduction and convection. So here we have kind of the remaining heat energy that's heating our atmosphere, and some of it's escaping back out into space. So when I look at heat transfer, I'm looking at conduction, convection, radiation, where radiation is simply heat that's traveling through a medium. Conduction, I'm talking about heat transfer through direct contact, and convection is simply saying that a hotter molecule or a hotter object is going to rise, and a less hot, presuming it's the same object, is going to sink, that we create these heat transferring cycles or systems here. So the result of these different angles of incoming solar radiation, we can view this when we view what's called an isotherm. That in June, when the northern hemisphere, 23.5 degrees, is getting the most direct sunlight, you see that land is heating up substantially more than that of water. So these isotherms are lines of equal temperature. That here I have land, these are the areas that are receiving the greatest amount of heat energy, the greatest intensity, and they're going to heat up, correspond the directness of sunlight. So here I have land heating up. Notice that the oceans themselves are receiving direct sunlight, but they have a greater specific heat that's going to change their ability or the rate at which they're heating up. And then here we have a picture of an isotherm in January. And notice the southern hemisphere, the continents are being affected by the insolation a little differently. It's simply saying that the direct sunlight has shifted. So when I kind of dance these back and forth, you get a better idea as to how the isotherms, well, let's just say they oscillate seasonally. During our northern hemisphere summer, the northern hemisphere is receiving more direct sunlight, and therefore land is going to heat up more. And in the southern hemisphere, notice that the southern hemisphere continents are going to heat up more. And look at these isotherms that we find in the northern hemisphere. We get a much greater temperature difference here, and these are just getting colder as we move toward the poles. So these isotherms kind of help paint this picture of a regulatory pattern of temperatures that change. So here we can look at what's happening. Sunlight comes in, and insolation here, incoming solar radiation, is going to reflect from tops of clouds and re-radiate back into space. It's this very heat energy that we're going to be looking at here that's going to be driving weather systems. So the sun's light is absorbed here. I've got a picture at nighttime. Dark colors are going to absorb that heat energy and then re-radiate it back into space, back into the atmosphere, even after the sun is set. So at night, the land is giving off this heat, and the heat it's giving off is considered infrared or long wave radiation. But now we can start looking at light and dark. White is a better reflector than dark. Lighter colors have a greater albedo, and we'll make sense of this term again. Has a greater albedo than darker colors. Dark colors, brown, black, green, they absorb insolation and heat up differently than light-colored objects. So albedo here is a measure of an object's ability to reflect sunlight. In astronomy, many planetary bodies in the solar system are visible due to the reflection of sun's light from their surfaces. It's the reason why we see planets, right? They're not emitting light. Only the sun in our solar system is emitting light. So the reason why we see these is because they are reflecting light from their surfaces. Their atmospheres and or surfaces are, light photons are bouncing off of them. So the measurement of albedo is a subjective scale. 0 implies complete darkness, and 1 implies that it's completely bright. For example, fresh snow can have an albedo of 0.9, which we would call 90% of that light is reflected, where coal, a very dark object, has an albedo of 0.1. The Earth has varying albedo scores. Different locations have different abilities to reflect or absorb light. So on average, the Earth's albedo is around 30%. Some objects have lower albedo scores than expected. For example, our moon has a very low albedo score of 0.12, which would be 12% of the light is reflected. So before we move into this last topic, we're really making sure we're staying focused on what it is we're looking at. We're looking at how sunlight is behaving once it comes into contact with an object, whether it's land or water, and then how is the heat then redisseminated into the atmosphere. We're really we're studying what is the light doing and why is it doing it. So here we can take a look here at the inverse square law, that the further I get from an object that's emitting light, the further I get from a light source, the intensity is going to decrease by its inverse squared. So a watt is a measure of power, or the amount of energy that something generates or uses over time. So if I look at this light here, that the further I get from it, the less intense that light's going to be. So let's just apply the concept of an inverse square. If I have this light and it 1 meter away, its intensity is 8 watts per meter squared. So this is just an example problem. That if I go twice as far, so now I look at how much intensity is when it's 2 meters away, it's going to be 1/4 the intensity. And here's how I know that. Because it's an inverse square, if it's twice the distance, it's going to have 1/4 the total intensity. So 1/4 of 8, right? 8 watts per meter squared at 1 meter, it's only going to have 2 watts per meter squared of intensity twice as far. So if it's 2 times further, it's going to be 1/4 the intensity. So 1/4 of 8 is 2 watts per meter squared. So here are some practice problems I want to make sure you have a chance to go through. But let's reiterate the basics here. The further one is from a light source, the less intense the light energy, right, in watts per meter squared. Therefore, the closer, the greater. If 100 watts per meter squared of energy is received at 50,000 miles or 50 million miles away from the source, then it would only be 12.5 watts per meter squared of light energy received twice as far. Right? Being twice as far, it's only 1/4 the intensity. So 1/4 of 50 million would be 12.5 watts per meter squared. If it's 3 times further, it would only have 1/9 the original intensity. And if it were 4 times further, it would be 1/16 the intensity. And I can use these the opposite way. If I go something that's 3 times closer, it would be 9 times the intensity. If it were 4 times closer, it would be 16 times the intensity. And if it were half the distance, it would be 4 times more intense. So here's a couple practice problems you can solve on your own. A light bulb is 10 meters away from an object that is receiving 2 watts per meter squared. How much intensity would the object receive if it were 20 meters away from the light source? Well, since it's 2 times further, it receives 1/4 the intensity. So 1/4 of 2 watts per meter squared equals 0.5 watts per meter squared. A planet that is 75 million miles away from a local star receives 36 watts per meter squared of light. How much intensity would a planet that is 225 million miles away from the same star receive? Well, if it's 3 times further, it would be receiving 1/9 the intensity. So 1/9 of 36 is 4 watts per meter squared. There we have it. We're looking at the total amount of sunlight energy that's entering our atmosphere. It's either absorbed, it's either reflected, and what happens when it is reflected and then reabsorbed by atmospheric gases that we call greenhouse gases, a very natural process. But in the end, we're looking at the heat energy that's coming and going from the planet, and that heat is being driven by the sun.